We'll begin our discussion of sections 4.7, and then in our second video will be 8.5. All it is the same method. One's a lower order DE, one's a higher order. Okay, so let's start. These are called Koshi Euler. Those are two mathematicians. You guys have seen Euler before, even in the semester, and several throughout. Cauchy is another mathematician. That's how you say it, Koshi. When I have a Koshi Euler DE, the difference is with what we've been working with is we still have this like linear relationship among our y's, right? That's still linear. We still have linear, everything else does x. The only thing that has changed now is that we have this x to the n minus 1, and it counts all the way down to the x, and then the y term has nothing. Example of a Cauchy Euler homogeneous ODE, if you take a look at this one, notice that these are all, make it linear, right? And then the other thing, 3x, x to the third, x to the second, x to the first, no x. That makes it a Cauchy Euler. It's a linear, and then it also counts down in exponents. So the method for this, I'm going to do it in general rule here. It's all typed out for you so you can see it. We are going to make a guess here, just like in the other ones, right? We made an e to the x guess. Now we're going to do an x to the m guess. So x being our independent variable to some power. If I do that and I take the derivative of that, the m comes down. It's just the power rule. M comes down, then I minus 1. And then the second one, the m minus 1 comes down, and then I lower it again, down to 2. So we have those two things. What we do now is we go back to this DE that we're working with, and we're going to plug everywhere there is a y double prime, y prime, and a y, we're going to plug those in. So we plug them in. They're in red there. If you multiply it out, we have x squared times x to the m minus 2. We add exponents. So this is x m minus 2 plus 2, which just gets us x to the m. So notice here in every one of these terms, we have an x to the m, all three terms. So we can factor that x to the m out, and we have this quadratic that's left inside. They put those two terms together. All they did is factor an m out and put the b minus a. Well, at this point, this equation, when I have x to the m times something else equals 0, we would take that x to the m and we'd set it equal to 0, and we'd take that something else and set it equal to 0. Well, this only works if x is 0, right? That's the only time we can get 0 from that. So this is a trivial solution, x equals 0. I'm not going to worry about that every time. I'm going to focus on this part. This is going to be some kind of polynomial, and we're going to solve that polynomial. Now, we have different cases just like that other method. If our numbers are real, then my solution, I just do x to the first solution and x to the second solution, and then we get our general solution by throwing some constants in front of it, just like the other method. If m1 equals m2, meaning we have repeated roots, I get x to the m, 1, and then the other root I get xm to the m2, but I put an L in an x. I create my general solution the same way. They're just new rules. We're not going to go about the theory of why these are true. We're just going to trust it. Y1, so this is if we have an imaginary number. Imaginary numbers look like alpha plus or minus beta I. I get two solutions from that. I have this one, x to the alpha cosine beta ln x, and then I have the other one, which is just a sine. Then we put those together for our general form. So these are rules that you'd want to keep. This is something, if you're allowed a note card on your tests, maybe you could generalize this somehow quickly. That way you have a reminder of what your solution should look like. Let's get a couple examples under our belt. Example 1 here. So first thing, it's linear, right? Y, second derivative, first derivative, 1y, there are no other y's. No y squared, it's nothing weird. And then also, 4t squared, 8t, no t. This is, sorry for the zoom there, it does that sometimes with my palm. This is a Cauchy Euler, DE. All right, so when it is Cauchy Euler, we let x equal, not x, but y equal, here's the thing that I mess up a lot on. This is not an x, it's a t. And I'll put an x there, and then I go plug everything in, and nothing makes sense, and then I'm like, oh, now I have to go back and erase. So instead of x to the m, we're going to do t to the m. If you do an x, you're going to catch yourself when you try to plug it in. and you got t's and x's. Okay, so y prime, I got m, t, m minus 1. These are going to be the same every single time. I do it every time. I don't memorize it. I just don't care for memorization. This is m squared minus m, t to the m minus 2. Because I go down 1 again. The m minus 1 came down and multiplied with m to give me m squared minus m. Then I have that t to the m minus 2. Okay, this part I would always just write small. We are going to plug those into our dE. So we get 4t squared. This is where, like, if I plugged in m squared minus m and then times t to the m minus 2, when I would try to work that out after I write down everything, I would realize that I have t's and x's. And then I would have to erase my x's and put t's. That happens to me often, so it may happen to you. Just fix it. All right, we replace y prime with m t to the m minus 1, and then plus y, which is t to the m. All right, we multiply here, and you're going to see this thing happens every time. The 4 goes through, so I'm going to do 4m squared minus 4m, and I'm going to throw that in parentheses, and I'm going to multiply this t squared times tm minus 2. This leaves me with just a t to the m. The 2 and minus 2 add together to get me a 0. Same thing here. All right, I get 8m times t to the m. And then this last one, I like to put a 1 here. It helps me not forget it. Notice every single term here has a t to the m. So that means that I can factor out t to the m. So I got 4m squared minus 4m plus 8m plus 1. That's why I write the 1. A lot of people will forget it there. Okay, this ends up being t to the nth, 4m squared plus 4m plus 1 equals 0. Now this is where that trivial solution thing comes in. Tm equals 0. This is trivial. And then we also have 4m squared plus 4m plus 1, and we solve this now. That factors. I'm not going to spend our video time doing algebra, but this factors is a quadratic. 2m plus 1 squared equals 0. If I solve this now, I take 2m plus 1, I set it equal to 0, now I solve for 1. We get negative 1/2. All right, this is a repeated root. So since it is repeated, if we look at our notes from above, I have two solutions. I have y sub 1, sorry, let me mute my computer. It was an email. I get x to the negative 1/2, and I get y sub 2, which is x to the negative 1/2, times, let me fix that 2 there, times ln of x. Oh, and then I did it. They're not x's, they are t's. Ln of t. That's what the rules above say. So the general solution for this is y equals c1, t to the negative 1/2, plus c2, t to the negative 1/2, times ln of t. That's my general solution to that problem. I don't mind this method. I think it's pretty straightforward. The worst part for you is going to be the solving the polynomial after the fact. That's my guess that it will be, because above doesn't, the only calculus is taking the first and second derivative of your y. Okay, let's get another example. So there's our repeated roots. That's what we do when we have repeated. All right, let's take this one. I see, okay, you should verify that it's Cauchy Euler. Okay, it is linear because of the y's. And then I have t squared, t to the first, no t. Okay, so we get, I'm going to make my guess to be t again to the x. All right, that means not to the x, but to the m. All right, that tells me y prime is mt to the m minus 1. And then y double prime is going to be m squared minus m. That's bringing m minus 1 down and multiplying by it. And then I bring down my exponent by 1. Now I replace, so the dE. I got t squared times my double derivative, so m squared minus m times t to the m minus 2, plus t times y prime, m times t m minus 1, and then minus 4 times t to the m. That equals 0. All right, m squared minus m, I multiply my t's together, I get t to the m. I want that to happen. Here, I got an m, I multiply my t's together, I got t to the m. Then I'm going to put, this is feels silly, but I'm going to put minus 4 in parentheses and then t to the m. But I don't want to miss that minus, that's why I do that. Notice that t to the m, We got one right here, here, and here. So that means we can factor t to the m out, leaving us with m squared minus m plus m minus 4 equals 0. That t to the m is my trivial solution, so I just focus on the polynomial inside. The m's cancel, and I get m squared minus 4. This tells me if I add 4 and take the square root, be careful with this, it's a plus or minus 2. So y1, since these are just real numbers, I get t, almost at x, to the second, and then y sub 2 is going to be t to the negative 2, which means our general solution is y equals c1 t2 plus c2 t to the negative 2. So there's our general solution. All right. I have one more example for this video. It's going to be the same process. So notice it is linear. The y double prime, y, no other y's. And then it also is Cauchy Euler. We should probably state that every time. I didn't on the last problem, but Cauchy Euler dE. And this will tell me, hey, I'm about to start this method. Okay, this method tells me to do y equals, this one is x to the m. So y prime is m times x to the m minus 1, and then y double prime will be the same thing. If you want to memorize these, that's great. I am not great at memorization. I forget things a lot, so I like to come up with those every single time. All right, now I plug that in. X squared times y double prime, which is m squared minus m, times x to the m minus 2, minus x times y double prime, and then plus 5 times x to the m. All right, so we get m squared minus m times x to the m minus m, I'm going to do a plus negative m, x to the m, plus, and I'm going to put 5 in parentheses just to help my brain out, equals 0. These take a lot of writing. My hands cramp a lot doing DE and Calc 3, so if you had Calc 3 recently too, you understand. There's a lot of writing. Unfortunately, there just is. All right, x to the m factors out. We get m squared minus 2m. I added my m's together plus 5, right? X to the m is my trivial solution, so I only need to focus on m squared minus 2m plus 5. Right, this is a quadratic. It does not factor, so I am going to use the quadratic formula, which is negative b, so it's plus 2, plus or minus the square root of, okay, it's b squared, that's going to be a 4 minus 4 times 1 times 5, all over 2a, in this case, that's just 2 times 1. So we get 2 plus or minus the square root of negative 16 over 2, right? That is equal to 2 plus or minus, and then that negative 16 square root, hopefully you remember this from college algebra, it is 4i, not a vector. I'm so used to putting a vector. That is a complex number. Over 2. This is equal to 1 plus or minus 2i. To be able to divide by 2, hopefully you remember from college algebra, it has to go in both. Since this is imaginary, I do alpha equals 1, beta equals 2. All right, and then we have these definitions. So y1 is equal to x to the alpha cosine beta ln of x. Or, yes, that's it. And then, so let's plug that in. Y sub 1 equals x to the 1 cosine 2 ln of x. Y sub 2, the formula for that is x sub x to the alpha sine beta ln of x. So y sub 2 is equal to x to the first sine 2 ln of x. Now, I don't know if you remember this, but there is a power rule for logarithms too. Ln of the x, I can bring that 2 up, becomes ln x squared. I think it looks cleaner. I don't, just kind of. So I write my general solution now. General solution is y equals c1 x cosine, and I'm going to change that to ln of x squared. It looks better to me. Plus c2, if you don't do that, I wouldn't count off or anything. X sine ln of x squared. There's my general solution. So again, this method, it really just covers algebra. Some problems can get pretty tricky with what you have to solve in the parentheses. If you need to use a calculator to find roots, that's okay for me. I am looking at this DE method, not your algebra. Unfortunately, to get the actual answer, you have to know some algebra. but I don't need any crazy simplifications. I don't need you to solve a fourth degree polynomial in your head using something. If I do give you some kind of high degree polynomial, it will be factorable in some way. I won't make you use some crazy method for it or something like that. You'll see more of what I'm talking about in the next video. All right, so that's Cauchy Euler. Cauchy Euler.